So applications of double integrals. So we're gonna do a couple of these. We're not gonna do all of the applications. I just want to do the ones I like the most to do, and the ones that are very similar to what you guys should have done in a single variable. So the first one is density and mass. So suppose we have a mass, a thin plate called the lambda with constant density. So we have got a little pipe here, right? So this is the region in the xy plane that is density at the point D, given by the function phi of xy. So the theory goes that if we were to find the area of this point in D with a function phi equaling phi of xy, then the sum of all the areas put together in 3 dimensions gives us this, which more importantly finds us the mass of the total mass of the object, which is the crazy part. So physicists use this a lot to find mass of objects and particles in 3 dimensions, and in actual space. So we take the limit as k goes infinity, L goes infinity. We find the integral of the total mass, and we also something called the total charge as well. So the total charge of electricity, which is one of the key things, the reason why we care about multivariable calculus is how electricity is done and how magnetism is actually created with the vector fields, is given by this. So the total charge of electron, or charge, like if you plug it in to your socket, is equal to this integral here. And that is what we're going to try right now. So let's see. So the charge is distributed over the region D created by y equals 1 and y equals 1 minus x, so that the charge density at xy at any given point is equal to just x times y. Final total charge in coulombs, C. So coulombs is just, if you guys are not sure, right, is just the units of the charge itself. Okay, so first off, let's just graph what we have. So y equals 1, so which is right here. And then y equals 1 minus x. So this is our region right here. This is our D. So if we integrate this way, therefore x is going to go from 0 to 1, and y is going to go from 1 minus x to 1 of our function xy. dy dx, no polar, right? So we're just getting straight to x and y. So first integrate with respect to y. This is going to be y squared over 2x, evaluated at 1 minus x and 1. Yep. So plug in 1, we get 1/2 minus, plug this in, we get x, and then 1 minus x squared over 2. So I just distribute this to make it easier for myself. And this is what I got. It's supposed to be plus. This is plus as a minus here. Over 2. And then if I distribute the negative plate, put everything all into one of them. I'll just bring the 1/2 out. X's cancel, which is nice, and you get negative 2x squared minus x to the third. And we're integrating this from 0 to 1 dx. Right? This makes it positive. This is the positive one. Yeah, this makes it positive. That makes it negative. And these x's cancel. Okay, so integrate this. evaluate at 0, 1 times the 1/2 at the end. We get 1/2. Plug in 1, get 2/3 minus 1/4. Plug in 0, it just goes away. So we just end up being this part here. Let's see. So 2/3 would be 12. So 5/3, 5/12 times 1/2. So 5/24. So that's the charge itself. Yep. So interesting question. Now the next one is probably going to be your favorites because there's so much integration. So I know you guys love integration. So moments and center of mass, which is also another concept you guys probably saw in single variable. So suppose we want to figure out, given a region D, and we want to find a density function such that we want to find the center of the mass of this, right? So the easiest way to figure out is, what it means by center of mass is, I don't know if you guys are younger, right? You kind of like, well, what's the center of mass of this, right? So if it's exact center, balance it out. That's what the center of mass ends up, what that means itself, of a region in space. Now, the problem with, because of this takes forever, is because we have to find the moment of both x and y, because it's in the xy plane. So what point here, for instance, respect x and y, does it go into? So that ends up looking like this. So the coordinates, x bar and y bar, the center mass occupying the region D, have the density functions looking like this, where it's 1/m times the double integral of x times the function, and then the y coordinate is the exact same, but we just multiply by y itself. Now, it's already bad enough we have to do two integrals. Well, guess what? We also have to find the mass of the entire surface or the object, and the mass is another double integral. So to do center of masses, we actually have to do 3 integrals to do so. So you will get plenty of practice for integration when it comes to center of mass. Okay. So why don't we try an example out how this would work out? So find the mass and center of mass. So it doesn't matter, right? We need to find the mass anyways. So find the mass, center mass of a triangle lemma at the vertices 0, 0, 1, 0, and 2, 0, or 0, 2, if the density function is equal to 1 plus 3x plus y. Okay, so let's just plot what we have. So vertices 0, 0, 0, 2, and what's the last one? 1, 0. So here's our region. We want to find the center mass of this surface here. Okay. So first off, we got to find what is this equation will look like from 2 to 1, right? And that's just going, you can find the slope if you want. So y equals 1, 2, down 2 over 1, so negative 2x, and plus 2, right? Because the y-intercept is at 2. So this is our function right there. So if you take the integral, it's going to go from here to here. So x is from 0 to 1, and y is from 0 to negative 2x plus 2. Now, like I said, we have to do 3 integrals. So first, we do the mass, because that's the only thing we can do before anything else. So put m for mass here. So the mass of the object is going to be the double integral from 0 to 1 and 0 to negative 2x plus 2 of our function here. Okay. All right, take the integral with respect to y. I'm just going to squeeze it over here, just as you can tell, practice sake. So y plus 3xy plus y squared over 2. Evaluate at 0 and negative 2x plus 2. Okay, so this ends up being negative 2x plus 2 plus 3 times x times negative 2x plus 2 plus all of this squared over 2. And then 0 goes away because plug in 0 over you see y, and all is gone, right? And this is squared, sorry. Squared. Okay. Now this looks like a horrible mess. So this is the one part like I said earlier, I may skip. Distribute and then FOIL in out. The 2 actually goes away kind of nicely. You can even factor out the 2 out. So it'll be 4 over 2, so it just gives a 2. But after all of this distributed property, and you could just check my work, I get something kind of nice. It ends up looking like this. Which is super nice, right? So take the integral. And we just get 8/3. So that's our mass. So that's the first part. Okay. All right, now we have the fun part. Let's do the first one, the x coordinate. All right, so for the x coordinate, it's going to be, again, double integral. But now this time it's going to be the same function multiplied by x. So this times x. Okay. Same process, take integral with respect to y first. And again, plugging in everything, only for y though. Ooh, I'm missing something right there. Missing a y there. So plug in everywhere you see y's. Okay. Again, you can check my work. I think this like did this twice just to make sure I got everything correctly. It's a bit painful. So again, multiplying, distributing, foiling, multiplying by x and all that fun stuff. You get rough. I believe, hopefully I get the same thing you guys get. It took me a while to break all that down to that. Which is kind of because it's almost identically to this, right? Just multiply by x, you get the same thing. It's pretty interesting. All right, so integrating this. Gives us that. between 1 and 0. So we just get 1. So therefore, my x-coordinate, because we're not in it, remember, it's the integral of what we just did times 1 over the mass. So this times 1 over that, which just gives us 3 over 8. So that's got our x-coordinate. So we just got to do one more time to get our y-coordinate, and finally we're done of the center of mass. Everybody tired with integration so far? Everybody loves integration, right? Okay. One more time, and now it's y times everything. So it gets a little harder because a lot more fractions involved as well. Okay. Okay. So same process. But now it's y times all of this. Yeah. So now this one integral is just going to be doing some stuff, right? So it's going to be y squared plus 3x all over 2, sorry, squared over 2 plus y to the third over 3. Right. Okay, so plugging in this in for y now. And again, you could either trust me. So plug it in to the cube and to here. And after a lot of work, I get something like this. And then finally, integrate with respect to x. So 0 goes away, so we just plug in 1. So plug in 1 everywhere, we get 14 over 3 minus 3 minus 2/3 plus 10/12. And in fact, I do get a positive, surprisingly. I get a positive 11 over 6. And just like we did here, we have to multiply this by 1 over this. So we multiply by 3 over 8. So this ends up being 2, 1. So 11 over 16 is the y-coordinate. So our mass is 8/3, and our center of mass is the point 3 over 8, comma 11 over 16. So that's our balancing point. It's pretty cool. I always thought that was so 3/8 and 11/16. So at this point right here in our region, approximately, is where it's completely balanced. That's the center of it. So you can balance it at that particular point. I thought it was pretty cool when it comes to center of mass. All right. One more. But trust me, this one's easier. So the density at any point in a semicircle is proportional to the distance from the center of the circle. Find the center of mass of it. So we have a semicircle. and we want to find the center of mass of it somewhere here, right? So it's somewhere over there. So this is x squared plus y squared equals some a squared. So a squared means, right, the distance, not the distance, but the radius changes how we want it to be. So therefore, our distance is going to be equal to the square root of x squared plus y squared. So since we have x squared plus y squared, polar coordinates. So we have theta and r. This time theta will go from 0 to pi. And our radius goes from 0 to a, an arbitrary value. So therefore, our equation, our d distance, is just going to be r. Super nice, right? So to find the center of mass, first we got to find the, find the center of the, center mass. We got to find the mass. So take the double integral of 0 to pi and 0 to a of just r times r dr d theta. Like I said, don't forget that extra r when we go from polar. So there's r squared. So integrating r squared gives you r to the third over 3, evaluated as 0 and a, which just gives us a to the third over 3. So integral from 0 to pi of a to the third over 3 theta is just itself, right? So this ends up being a to the third pi over 3. Right? Then we get the x and y. So trust me, these are actually much easier to deal with. So the x is we're gonna multiply by another x. So we're gonna have same bounds of, well, in case just r squared, right? R squared times x. So remember, x equals that. So we have r cubed cosine theta dr d theta. So this is r to the fourth over 4 cosine theta divided from 0 to a. So take integral from 0 to pi, and I could just put this on the outside. That's sine. And this is the most interesting part of all. So I plug in pi, that gives me 0. Plug in 0, I get 0. Huh. So the x coordinate is actually x equals 0. So it only cares about the y-axis. So it's somewhere over here, which makes sense, right? Because it's like, very symmetric. So hopefully we don't get 0 for y. That'd be weird. Okay, so same thing. Now remember, r at y is just r cosine, so r to the cubed. So now just sine and mimic exactly what we just did earlier. So I'm just going to quickly do that integral because it's the same pattern. Oh, this is a 4. No wonder I confused myself. 4 sine theta 4. No, doesn't matter, but just for practice purposes. This time it would matter. Okay, integral of sine is negative cosine. Okay, so cosine of pi is -1. So negative negative makes it positive. And cosine of 0 is 1, so this would be -1. So this ends up being 2. So it'd be 2 times a to the 4th over 4, which ends just up being a to the 4th over 2. Okay. And don't forget, we also got to multiply by the reciprocal of this. So we just get a, so 3a over 2 pi. And that's our x coordinate. So our center of mass is the point 0, comma 3a over 2 pi. Anybody having fun yet? Good. Questions? Good. All right. Moments of inertia. There's also a nice little object to go by. So moments of inertia is another way for object resisting change in angular rotation. So if you rotate something, basically it's the force or resistance going in the opposite direction. It what does not want to move in that direction. That's what's looking at. So you're forcing it, and that resistance or that force that's going opposite is what moment of inertia actually is. Okay. So the moment of inertia of a particle of mass m about the axis is mr squared, where r is the distance to the axis. As before, phi of xy is a density function over the region r d. And again, just like the moment of mass, we have 2, because again, this goes into both directions, right? It's not always going to be up or down. It could be the moment of inertia is like this way, right? At an angle. Okay. You can think of like a waves in a boat, right? So waves doesn't always go this way or this way. It can go northeast. So the waves are pushing it this way while the boat wants to go straight. So that's your moment of inertia going into the XY coordinates. Okay. So it's very similar to the center of mass. The only difference is instead of x and y, it's y squared and x squared. However, the key thing is the inertia in the x coordinate is y squared, and the inertia in the y is x squared. Just because they swap places. So that's one thing you got to be very careful of. Okay. Okay. But there's your hint, right? We have x squared and y squared. So probably polar is going to be the way to go for these type of questions. So find the moment of inertia of a disk, x equals y squared, with density function 2 phi centered at the origin and radius 3a. So there we go. We have a disk. And this radius is 3a. Okay, so therefore, if we go to polar coordinates, it goes all the way around, right? It didn't tell me if it's only in the upper half or the lower half. It's the entire portion all the way around. So let's do the first one. Inertia with respect to x. So this is the double integral from 0 to 2 pi, and then 0 to 3a. Now, according to our equation, it's y squared times the phi function. So this is going to be constant, so it'd be 2 pi there, times y squared. And y squared is r squared cosine squared, right? And then times the r because it's go polar. So it'd be r cubed sine squared theta, dr d theta. All right, take the integral. Remember, this is constant, so we just r to the fourth over 4 of sine squared theta, evaluate at 0 and 3a, and then 2 phi is still fixed. All right, plugging this in. 3 times 3 is 9, times 3 is 27, 27 times 3 is 81. So get 81, a to the third, right, fourth over 4 sine squared theta, theta. And again, if you noticed, there's our old buddy again, right? So this is all a constant, so I'm just going to bring this all to the outside, right? This is actually the constant itself. So simplifying this a little bit, the 2's cancel, so we're just going to get 81 over 2 pi. So this is being, so again, this integral ends up being theta over 2 plus sine of 2 pi over 4, evaluated at 0 and 2 pi. And it doesn't matter if it's 2 pi or 0, this is gone. 0, that's gone. So really it just ends up being, just plug in 2 pi into here. So it just gives you pi. So it's pi times that bad boy there. So we just get, so the moment of inertia on the x coordinate is just going to be 81 pi a to the fourth phi all over 2. So that's the resistance in the x coordinate plane. So here's your x credit. Find that. And same thing, just email to me. And let's say before Thursday. Because I pretty much gave the template to do so. Yeah, there you go. Okay. So now let's go into what I really like, because I've taught stats pretty much every time I teach. And so that goes into my favorite part is probability. So probability is given a pair of continuous random variables x and y, the joint density function. So this is one of the hardest parts of probability, is figure out how to do probabilities. And the cool thing is you actually see how differentiable and integration goes into probability. Oh, sorry. It's not just multiplying two numbers together. And that's the cool part, because you're actually doing integrals over curves. So for example, like the normal distribution curve, to find the probabilities, you actually find the area underneath the curve itself. So kind of like we're figuring out here, the only difference is we have a joint density function, which is a little different. So given the probability of x and y, the region is just a double integral of a regular function dA. Now here's a little fun thing. A little sum of probabilities, because this actually comes into play big, is the sum of all the probabilities must be greater than or equal to 0. So you should never get a negative answer, which is a big no-no. And they all equal 1. So the integral, but the indefinite integrals of the limits equal 1 no matter what. Okay, that's one key thing. So they have to be greater than or equal to 0. And all their sums, so since it's a summation is an integral, equals 1. And that's actually, I'm going to do the next problem right now. All right. So if the joint density function for x and y is given to be that, it's a piecewise function, find the value of c, and then find the probability of x be greater than or equal to 8 and y is less than or equal to 4. Okay, so first we got to find c. So what constant there makes this true? Okay, so for a, according to our equation, is just going to be the integral over the region d. So in our region here is bounded between 0 and 10 for x and 0 and 10 for y. So it's a rectangular region, right, of 10 by 10. That's kind of nice. So integral from 0 to 10, integral from 0 to 10 of our function. So c times 3x plus y dy dx. So c is a constant, so I'm just going to bring that out. So integral of this is going to be 3xy plus y squared over 2, evaluated at 0 and 10, times c. So now just plugging in 10 and for y. So 10 times 3 is 30. 10 squared is 100, divided by 2 is 50. And there we go. And now just integrate with respect to x. So x squared, I think this should be 15. 50x, evaluate again 0 and 10. So again, 10 squared is 100 times 15, it should give you 1500 plus 500 equals 2000. Okay. All right, so now remember times c, so this is going to be equal to 2000 times c. Now the question is, how do we solve for c? Now this goes back to this right there. So our bounds are from 0 to 10. So no matter what it is, this function with it when it comes to this region must equal 1 if you use the entire region itself. So therefore, since we use the entire region itself, technically this integral equals 1, which means after doing all this portion, this equals 1. So c equals 1 out of 2000. There we go. Like I said earlier, it comes up the very first part automatically. All right. Now that we have that, now let's go to part B. This is the fun stuff. So this is what I wish I could do in statistics. Unfortunately, none of them taking calculus, so we can't go into this for our stuff when it comes to it. All right, so we want to find the integral. So now we know what c is. We're just going to plug that in. Of x to be greater or equal to 8 and y is less than or equal to 4. Okay, so x is greater than or equal to 8, so it's bounded between 8 and above. And I can't go any higher than 10, so it's from 8 to 10. And same thing when it comes to y. So y is max of 4, and it's bounded between 0 and 10, so lower is 0. Our function, so I'll just leave this on the outside. So this is 2000, 1 over 2000 c of our function itself. Like that. Okay, same process, integrate respect to x, or sorry, y first. Do this y first. So that makes more difference, right? So 4 times 3 is going to be 12. 4 squared is 16. 16 divided by 2 is 8. So now this is evaluated from 8 to 10 of times 1 over 2000. So this is going to be x squared times 6 plus 8x, evaluated at 8 and 10. All right, so 10 squared is 100, so 600 plus 80. 8 squared is 64. 64 times 3 is 384. And the only reason I know this is because I did this earlier. And then this is 64. actually don't have this answer. Wait. Here we go. So this gives me 680 minus the sum of this. Where do I put a negative there? Is 448. So is equal to 232. And then don't forget, we also have to divide by 2000. So our true answer is approximately 0.116. Now, here's a cool thing when it comes to, all the biggest thing about when it comes to stats is how do you interpret this kind of stuff? So this represents is the probability of the variable x being greater than 8 and the probability of y being less than 4 is 0.16 is equal to 0.116. So depending on what x and y is, right, because x could be any arbitrary random variable. So x could be like number of cars and y could be some other joint one like cross streets. So the probability of both happening at the same time is equal to this. That's a cool part of probabilities is, you can do some elaborate probabilities because now you know integration, and same thing with differentiables. So there's some probabilities you actually take the derivative of, and then, set e equals 0 is the mode of minimize and maximize as well. So it's cool little fun stuff. Yeah. Now the biggest one is next one is something called expected value. But everybody good here? What we just did? Good. Right, so expected value. So generally, the expected value of random variable is the mean of the variable output over time. And that's actually correct. So the expected value is what's the average of both of them put together or of one together. But since we're doing two, x and y is a joint one, we're going to find two of them. So when is the mean of the x and when is the mean of the y? But the cool ones is that the two density functions are put together joints. It's not that fun if it's just a single one, but it's just going to be this one or that one, depending on what x and y is. But, notice they're the exact same either way. But since we're dealing with joint, we want to find out, what is the average going to be? Now, when it comes to expected, here comes my little rant of probability. This is done when it comes to betting. So what's the expected output I would get or the expected money I would make every single time I would bet over time, like the average. And that's what makes it pretty cool. You can also do this integration when it comes to what is it called? Life insurance. So, is the life insurance policy actually good for me? How much am I spending on every time I pay on a monthly output? So anything that goes over time and you're paying or you're going to buy is you could do an expected value on it, see if it's a good buy or not. So, if you do the lottery, a lot of times you can see what your expected output would be, and most of the time it's going to be negative, since the probability, winning the lottery is so low. You're just wasting money. Eventually, you'll waste as much money as the lottery itself, the output, and that's the crazy part. Unless it's some lotteries aren't fixed, but that's a cool thing. Is like, why waste all that money if you're eventually going to accumulate that into it? So it's a little fun when it comes to. I always use betting. We use our like casino money to find expected values in my classes. But how do we do this in multivariable? This is the fun stuff. So let's find the value or expected value of the x and y outputs above. Okay. Right. So we're going to use the same equations as above. Okay. So this time it's going to be the mean or the expected value of the x values is just going to be exactly what we just did times an x, and the y is going to be exactly what we just did times a y. So we're just going to do two of them itself. Okay. So mu1 is going to be 1 over 2000 times this integral from 0 to 10. 0 to 10, right? It's the entire region of times x. So it's going to be 3x squared plus xy dy dx. So integrate with respect to x, or sorry, with y first. So 3x squared y plus x y squared over 2, evaluated at 10 and 0. So this gives me 30x squared plus 50x. Take the integral of that. Gives me that. And then plug in 10. That's the same thing as 10 to the 4th power. 2, 3, 4. And 100 times 25. And then all over the 2000. And I get approximately, or not approximately, exactly 6.25. So the average of x is 6.25. So over time, you would get 6.25 over and over and over and over again. And now we do the same thing for the y's. But now we just multiply by y instead. So it's going to be 3xy plus y squared. So this integral is going to look a little different now. And now we're going to have fractions everywhere. So this is going to be 300 divided by 2 is 150. This is going to be 1,000. And then take the integral. Gives me that. So plug it in. Yeah. 2, 3, 4. So this I give about 3.92. So that's the average of the y's. So put together. So both density functions, you'll get an output on an average 6.25 and 3.92 on x, the x random variable and the y random variable.